Before we move on to these trickier substitutions, I would really encourage you to make sure you spent time thinking about those first 6 examples, that our process makes sense. What we're going to do in the next 2 examples will be very similar, though we'll have to throw in a little bit of a twist with our substitution in order to get the problem to work out correctly. It'll start off the same. We'll identify our interior function, and then we'll take the derivative of both sides of that substitution statement. And then we'll multiply both sides by ds. So what we're looking for now is how this statement, the result of this derivative statement, could match up with pieces in our integral, but we don't have an exact match. What we have is s to the 8th and ds, but what we have here is that du equals 9s to the 8th ds. So this 9 is a little bit of a problem because it doesn't match exactly. So what we'll do is divide that 9 over to the other side to get du over 9 is equal s to the 8th ds. So now we have an exact match for what's remaining in our problem, and we can complete our integral statement. So this will become the integral of u to the 7th, and then in place of s to the 8th ds, we're going to be substituting in du over 9. In the first six examples, in every case we just substituted du here, but again, since that du statement didn't match up exactly with our problem, we had to modify it slightly, in this case by dividing the 9 to the other side, to get something that matched up exactly with those 2 pieces that were left over. We could rewrite this by bringing that 1/9 out to the front, since it's just a constant and the indefinite integral doesn't impact it. So we would get 1/9 times the integral of u to the 7th du, or 1/9 times u to the 8th over 8, plus some constant c, which would become 1 plus s to the 9th, raised to the 8th power, over 72, by multiplying our 9 times 8, plus that constant c. So again, our process here was very similar, except that we had to get a little more creative with this du substitution in order to get something that matched our problem exactly. We'll see that happening again in our next example. Here we'll want to substitute u equals 7 plus e to the 5x. Taking the derivative of both sides will give us e to the 5x times the derivative of that interior function, so times the derivative of 5x, or 5e to the 5x, which means that du will equal 5e to the 5x dx. So in our problem up above, we have e to the 5x, and we have dx. So what's incorrect about this substitution statement would be that 5. So if we divide that to the other side, we would get du over 5 will equal e to the 5x dx. So now we have a substitution, a direct substitution that we can make. We can rewrite this as the integral of u squared. And then again, in place of e to the 5x dx, we'll be substituting du over 5. We can bring that factor out front. And then integrate this as 1/2 times u to the third over 3 plus some constant c. Let me go back for a second there. I wrote that as 1/2. That should be 1/5 because that was that same 1/5 that we brought down here. So 1/5 times u to the third over 3, and then replacing our u with that original substitution statement will give us 7 plus e to the 5x. That quantity cubed over taking 5 times 3, we would get 15. plus our constant c.